Assalamualaikum, bismillahirrahmanirrahim. Yes, hello everyone. So today we are going to be taking some problems in chapter number 6 for the book Chemical Process Safety by Daniel Kroll and Joseph Lower. And if you go back to my 4 videos before, you're going to see that we had made a good progression on our understanding on fires and explosions. And as you know, for fires there's a fire triangle, and we have flammability limits. So we need to consider how to identify the lower limit and the upper limit, and by that to know where is the flammability region. And this would also support us that if we know that there are going to be some flames, is there going to be an explosion, and if there is an explosion, how much damage is going to be caused by that explosion. And if there is some kind of an explosion, is that going to be causing some death? Is that going to be causing some damage to the houses surrounding that area at different locations and so on? Okay, great. So going to that, let's start solving the problems. 6.1. Estimate the flash point of a solution of 50% water and 50% methanol. So here, these problems are just some kind of training problems before getting to the real problems here. And the whole idea is that you just get an idea of how to solve getting the flash points before you get into the details of how to do the other real calculations. So 6.1 is asking about the flash point, okay, the flash point. And what do we have? We have 50% methanol, okay, so we have 50% methanol and we have 50% water, okay. So this is what we have here, 50% methanol and 50% water. So the first thing that if you want to go and look at the flash point of pure methanol, okay, looking at the flash point for pure methanol, you go to Appendix B, and in Appendix B you're going to see that the flash point for pure methanol is 11 degrees, which is equal to about 284.5 Kelvin. Great. Now, to get the idea, like I don't have pure methanol, right? I have methanol and water. And since I have methanol and water, that means it's like I need to know if I have this kind of mixture. If I need to know what is the effect of having more 50%, or if I can consider only the pressure, okay, only the pressure or the mole fraction of methanol only, I could have an idea about what? I could have an idea about its new flash point, okay? So let's go on solving it. So at the flash point, which is that here, okay, which is that here of 284.5 Kelvin, we have the Untying equation where ln P saturation is equal to A minus B over T plus C. I think so you already can recall it, and you can get these numbers from the tables. The tables are available online, they are available everywhere, okay. Divided by T minus 34.27, and on doing that, this is equal to 4.09, and then you're going to find that Psat is equal to 60.1 millimeter mercury. Okay, now that is the pressure, and instead of saying Psat, I'll say that is the pressure. That is the pressure that is contributing to the temperature that is at the flash point, okay, the temperature or the flash point temperature. So that is the pressure that is contributing to that. And so if we now want to calculate what was the partial pressure, because now we are considering like everything as pure methanol, right? So now considering the partial pressure and using the other Dalton's law equation, where the partial pressure is given by, if you can recall this, it is given by Pi is equal to Xi into Pi sat, okay? And Pi, because you're talking about the partial pressure thing, and in this case we have Pi sat, which is equal to, sat is saturation, I'm sure you know this, right? Is equal to Pi over Xi, okay? Pi over Xi. So what was Pi? Pi, it was the pressure that was contributing, or it is that is in a line and comes from that flash point temperature. So this flash point temperature, what was the pressure at that moment? It was 60.1. However, we are talking about what? That flash point temperature, which is for pure methanol. But we don't want to calculate at pure methanol. We want to calculate at 50% methanol. And to calculate at 50% methanol, we are finding here we are considering here the mole fraction, and considering here the mole fraction, I'm going to find the new PSAT, okay? I'm going to find the new pressure, and based on that pressure I'm going to find out what is now the corresponding flash point temperature. So in this case, this is equal to 100 millimeter mercury, and we were just going to go back and substitute for the same equation that I have here, 18.59 minus 3626.44 divided by T minus 34.3, and then I'm going to find out that my new temperature is equal to 297 Kelvin, and this is equal to 24.1 degrees centigrade. Great. So that was the easy way, that was the calculation of this problem here. And just to look at what was the previous temperature. Okay, so for pure methanol, the temperature was 11 degrees centigrade, and that was for pure methanol. However, because I have a mixture here of 50%, what happened to the flash point temperature? It became higher. And what does that mean? It means higher. It means that if you have 11 degrees here and you heat up methanol, this is where you heat up methanol, and while you're heating up, it should give you a flash here. Flash, that means you're talking about a very small flame that does not propagate. Okay, so fire here that does not propagate. Now, because we have only 50% of methanol, we need to heat it even more to get to this flame or to this fire point. Okay, that means as we have water with methanol, this makes it less susceptible to get fire, So I hopefully you got the idea. So now my mixture is, I'll put that in blue. So my mixture is less susceptible. I forgot the spelling of susceptible. Oh my god, susceptible to fire. Okay, great. So that was for problem 6.1. I will leave 6.2 for you so that you can solve it. It is exactly the same, and I think that you already got an idea of how to solve it. Great. So let's go and solve 6.3. Now 6.3 is also another example to train yourself. So estimate the LFL and the UFL of the following mixtures. And again, what is LFL? It is the lower flammability limit and the upper flammability limit of the following mixtures. Of course, we have many mixtures here. We are not going to do every one. All right, it will take a lot of time to do all of them, but we will go to do some of them here. And please concentrate that what we have here is a volume percentage. So all of these are in volume percentage. So let's go, for example, now for the first mixture. This is my first mixture. My first mixture has 0.5 hexane, 1 methane, 1% methane, 0.5% ethylene, and then 2%, and that's all. So what is my total combustibles? Even if I don't give you the total combustibles, you need to know that you need to calculate the total combustibles. Okay, so how did you get the total combustibles? It is 0.5 plus 1 plus 0.5. So these are the total combustibles. So if you want to calculate it, what is the total? It is 100. 0.5 plus 1 plus 0.5 plus 98 is 100. Okay, so most of it is air and the rest are these combustibles here. Now this is the volume percent that I have in my total system here. However, if I want to calculate the LFL and UFL, I need to get the fraction of volume percent. However, pair combustibles, okay, pair combustibles is like 0.5 divided by 2, 1 divided by 2, 0.5 divided by 2, and so on, right? So hopefully you got that, and let's solve it here. Let's solve it. Going and solving, so the first part I'm going to go for A. What I need to, as it said, I need to calculate the LFL and the UFL. Well, we already have the LFL and UFL for the pure substances, and you can get that from Appendix B. Okay, so you can get this from Appendix B. And where is Appendix B? You go to your book at page 646. You're going to find Appendix B, and then you're going to search. Okay, for example, hexane, what is the lower flammability limit? Is 1.2, and what is the upper flammability limit? Is 7.5. Okay, so it's 1.2 and 7.5. So here we say, for example, hexane, it is 1.2, the lower flammability limit, and 7.5. Okay, 7.5, that is the upper flammability limit, and so on. So you're going to continue and find out the flammability limits for all the compounds that we have here. So we have methane, it is 5 and 15, and then you have ethylene. Ethylene is 2.7 and 36. We have acetone, and acetone you have 2.6, 12.8 is the upper flammability limit, and the last component we have here is ethyl ether, and in ethyl ether I have the lower flammability limit is 1.9 and the upper flammability limit is 48. Great. So what I'll try to do now is to calculate the lower flammability limit. Okay, so what is the equation for low flammability limit? If you go back to equations, just for you to know, equation 6.2 and equation 6.3. So go back to these equations, and we already know those equations where LFL is equal to 1 over YI over LFLI. Okay, so we already have the lower flammability limit for each one of the components. However, we don't have the mole fraction. So here the mole fraction is the problem actually. It is the missing information that we need. How to get the mole fraction? So a simple calculation says that, well, I already have for case A, And in my case A, if you can recall what is case A, it is 0.5 of hexane, 1 of methane, and 0.5 of ethylene. Okay, so I'm going to write that. My hexane, it was 0.5, and that is volume percentage, of course. And for methane, I had it was 1, and for ethylene, it was 0.5. And the total combustibles here is 2. So now if I want to calculate my mole fraction, however, I'm going to calculate my mole fraction based on the total combustibles. Okay, so this is the idea. So this is 0.5 over 2, which is equal to 0.25, and this is 1 over 2, which is equal to 0.5, and that is 0.5 over 2, which is equal to 0.25. So what did I do? I divided 0.5 divided by 2, okay, and then 1 divided by 2, and then 0.5 divided by 2. So this is what we have done here, and we found our mole fractions. Now that we have found our mole fractions, we just need to substitute here to get our LFL. As simple as that. And in doing this, I think so I can do it up here. Okay, so this will be 1 over, I have some space, 1 over 0.25 divided by 1.2. Okay, let me put this like that. Okay, so it's 1 over 0.25 over 1.2 plus 0.5 divided by, so yi, if you can see, it's 0.5 here, and the LFL for methane, I get it from here, which is 5. Okay, for 5. I think so I'm going to do it down there, so it's just more space. So LFL is equal to 1 over yi over LFLi summation, so that is 1 divided by 0.25 divided by 1.2 plus 0.5 divided by 5 plus 0.25 divided by 2.7, and that is equal to 2.5%. okay, that is equal to 2.5%. So what is my lower flammability limit? It is 2.5%. It is 2.5%. What is my upper flammability limit? Very similarly, I'm going to calculate it in very similar fashion, and all the details I have here, this is 0.25 over 7.5 is the upper flammability limit, plus 0.5 over 15 is the upper flammability limit for methane, and then we have for ethylene ether 0.25 over 36, that is the upper flammability limit, and this is equal to 13.6%. 13.6%. So what did we find? We found our lower flammability limit and the upper flammability limit for our problem here. So I would guess that you can do the rest now, because they are exactly in a very similar fashion. It is just that you need to consider that, for example, now 2 here, we have 0.5, 1, and 0.5. So the total combustible is 2. Here we have 1, 1, 1. So the total combustible is 3. So the mole percent here is 1 divided by 3, 0.33, 0.33, 0.33. Okay. So you need to consider how to calculate the total combustible so that you don't confuse yourself. Okay. So just to get a feel of it. So what happened here? What happened? We have lower flammability limits individuals of what? Of 1.2, of 5, and 2.7. So 1.2, 5, and 2.7. It happened that now my new lower flammability limit is something like in between, which is 2.5%. Okay, it's in between. And again, we say this is the way how to do our calculation. However, experimentally, things could be different. Especially when you calculate the upper flammability limit. Through experience, you're going to find that it happens that it is very different. So this is just a guide for us to know how to get close to those values, but the experimental values, they are the ones which are really of accuracy that you can depend on. Okay, so that was for 6.3. That was 6.3. So let's go now for our next problem. We are going to solve 6.4. 6.4. Okay, we are going to solve 6.4. Great. In 6.4, it says, estimate the lower flammability limit and the upper flammability limit for problem 6.3a. We solved part A. I mean, not part A, this A mixture at 50 degrees, 75 degrees, and 100 degrees. And again, I'm going to solve it just at one temperature here. So what we are saying here, we are saying that we want to calculate LFL and UFL if we have a different temperature at 50 degrees. What do I mean by different temperature? Estimate the LFL and FL for the following mixtures. Here for the following mixtures, we assume that it was at 25 degrees centigrade. And here what we have is now is at 50 degrees centigrade. So will my LFL change with temperature when it goes from 25 to 50 degrees? Will my UFL change with temperature if it goes from 25 to 50 degrees? Similarly, then we are going to ask, if you want to solve the problem again, will my LFL change if it goes from 25 to 75? Will my UFL change if it goes 25 to 75? And similarly goes to 100 degrees. Okay, so we just need to go back to the problem that tells us if the temperature is changing, how we can calculate our new flammability limits. So if you go for the equations, if you go to the equations of 6.4 and 6.5, so these are the equations, and the equations, if you can recall them, the LFL for the new temperature is equal to LFL of the previous temperature minus 0.75 divided by the delta heat of combustion into T, the new temperature, minus my old temperature. Okay, so it is that simple equation there. And the same equation also applies for the upper flammability limit. Okay, 25 minus 0.75 of delta heat of combustion into T minus 25. Okay, so these are our two equations, and we just need to substitute. And I think so. The only thing that we need here, if we just concentrate, we have LFL at 25. We already found the LFL mixture, right? For the mixture. And we have our new temperature, which is 50 degrees. What we need is that delta heat of combustion. That's all. That's all. Oh, I have delta heat of combustion of every component, but I don't have delta heat of combustion of the mixture. Okay, we have the mole fraction and we have the delta heat combustion for each one, so we just can get the delta heat of the mixture. Okay, so we just need to get the delta heat of the mixture. And what do I mean by that? So simple calculation. So what do I have? I have my species or components. I have hexane, I have methane, and I have ethylene, and I have the delta heat of combustion of each one of them and the delta heat of combustion for each one of them. And let's consider here, we will consider kilojoules per mole or kilocalories per mole. Okay, so it depends on us actually what do we want, and I'm not sure if it depends on us, and we need to make sure about this delta H of combustion. Is it in kilocalories or it is in kilojoules? Okay, so let me make sure in a second, and if that is kilojoules or kilocalories per mole. So if you go back to your book, I think it's about page 235, where the section talks about flammability limit dependence on temperature, equation 6.4 and 6.5. It is written that the delta heat of combustion is the net heat of combustion, kilocalories per mole. Okay, so here we are talking about kilocalories per mole. Okay, so whatever you have given to you in the appendix B. In appendix B, it's okay. So in appendix B, it's given as kilojoules per mole. So you need to get the values in kilocalories per mole. Okay. So I would say that now this is given by the problem, by appendix B, and what I want here is the kilocalories per mole. Kilocalories per mole. Okay, and just to get the values and make sure that we know how to get these values, okay, just to know and make sure that how to get these values, let's go and find the delta heat of combustion for hexane. Okay, so it's like you're going to appendix B, and while you're going to appendix B and you say, okay, I want hexane. Here's hexane. What is my heat of combustion? My heat of combustion is minus 3855.2, and of course you know that you don't need to include the minus term here. Okay, so it is 3855.2. so I got my heat of combustion. What is the unit of that heat of combustion? It is kilojoules per mole. However, my equation wants it at kilocalories per mole. Okay, kilocalories. So you do your conversion here, where you divide by 4.2, something like that. Okay, so we go back here, and now we have our values. So that was 3855.2. Okay, and so on. You're going to get all your numbers here, and then you do your conversion, and you're going to get the kilocalories per mole, 191.7. 316.1. Okay, so we found them. And what you need as an additional information here, what we need is the mole fraction. And we already found our mole fraction. Let me write here, mole fraction. And we found that is 0.25 based on total combustibles, and that is 0.5, and that is 0.25. So all what you need to do is saying that, well, 921 multiplied by 0.25 plus 191.7 multiplied by 0.5 plus 316.1 multiplied by 0.25. So I'm getting the net heat of combustion, right? I'm getting the net of a heat of combustion. So here, the net heat of combustion, is equal to 0.25 into 921 plus 0.5 into 191.7 plus 0.25 into 316.1. Okay, and you're going to get that net heat of combustion is 405 kilocalories per mole. Great. So I have my 405 calories per mole. So what I need to do now, I'm going to substitute here. And we already have all the other information, and we are going to get our answer. So substituting, we will have LFL at 50 degrees centigrade. Okay, so LFL at 50 degrees centigrade is equal to LFL at 25 degrees, which was 2.5%, minus, I forgot the equation, by the way, minus 0.75 into T. Okay, so 0.75 into T, and T here is 50, minus 25 over delta heat of combustion, that was 405 calories. Okay, so if you do this, you're going to find your answer is going to be, I'm going to separate them, so you're going to see like this is like 0.2%, 5% minus 0.05. So this was the difference. This was the difference that I had because of what? Because of that change in temperature. So it just brought it down. It brought the volume percentage down. So it's saying that now even with a lower percentage, I'm going to get to the flammability limit. Why? Because you raised my temperature. So I have already more energy. So I need less gases so that I can get to my flammability region. Okay, so So 2.5 minus 0.05, that will be 2.45%. And you can see that this LFL did not really get affected a lot. And for my higher, the upper flammability limit at 50 degrees, this is going to be 13.6, and this minus, with a minus, another minus term, you're going to find out that it is going to be plus 0.05, and that is not really affected a lot. It will be 13.65%. So we can see with a small change in temperature, there was not a real big change, and the change was little. However, with bigger temperatures, things could be a little more, but the flammability regions did not change a lot. So we can say that the region became bigger. Okay, the region of flammability became bigger. Why? Because rather than saying 2.5, okay, so rather than saying only that my flammability region is between 2.5 and I would say that 2.5 is down here and 13.6, so that was my flammability region. Now my flammability region went little higher and little lower, so it became bigger. Why? Because you gave it more energy. So it becomes flammable now at a bigger region, Okay, so here's 2.45% and here's 13.65%. Okay, so this is the way how to calculate, and you can see how the region became bigger. However, you can still say that here the change is minor. Okay, the change is minor. It's very small. Beautiful. It's good always to analyze and see that you understand why did it change, and when it changed, it's not only why it happened, what effect it has, and you understand that effect. So this is what we're trying to do here. Okay, great. So that was 6.4. That was for 6.4, and now for 6.5, again another training question where it tells us to estimate the upper flammability limit of problem 6.3a, which is the one we solved, that mixture here, this mixture, at 1 atmospheric, 5, 10, and 20 atmospheric pressure. So let's do the one at 1 atmospheric pressure. 1 atmospheric pressure. Okay, so what was the initial pressure? I thought the initial pressure was 1 atmospheric pressure. So in problem 6.3a, we already said that was at 25 degrees and 1 atmospheric pressure. So definitely at 1 atmospheric pressure, we will have no change because it's the same pressure. So we mainly go to 5 atmospheric pressure and see what goes on there, right? Okay, great. So let's go and solve now 6.5. So that is 6.5. And now if you want to know which equations to use if you have change in pressure, for pressure you're going to use equation 6.6. And where equation 6 says there are two things, by the way. We said that for the lower flammability limit, the LFL will not change, only if it is really very low pressure, under 15 millimeters mercury absolute. So the LFL will not change. Okay, so that is my first part. So we don't worry now about the LFL. What about the UHL? Of course, that is equation 6.6. So UFL P, I will say here, the new pressure, is equal to my UFL, that at 1 atmospheric pressure, plus 20.6 into log P plus 1. Okay, and in this case, we need to just remember that P is in megapascals absolute. Okay, this is absolute pressure, megapascal. So great. What are the other values, just to make sure that we have them? So my UFL that was obtained from 6.3 was problem 6.63 was the UFL was 13.6%. And now what is my P at megapascal? Actually, what I have here, the value is 5 atmospheric pressure. If you go back, estimate the UFL at 5 atmospheric pressure. So at 5 atmospheric pressure, what is 5 atmospheric pressure to megapascal? So we just need a conversion here. So 1 atmospheric pressure is equal to 0.101325. I don't know if you can recall, 101.325 kilopascal. Okay, and now we have the megapascal. And if you have 5 atmospheric pressure, you just need to multiply this by 5. Okay, so you multiply this by 5. 0.01325 multiplied by 5 megapascal. And then you're going to take the log of that and so on. So that is like straightforward problem. And there's nothing difficult about it. So UFL P here, which is like 50 and 5 atmospheric, is equal to 13.6. Was it 13.6? Just to make sure. What was 63? Let's go back and see 63. Yes, it was 13.6. That's correct. I just wanted to make sure. So 13.6 plus 20.6 into log 0.507. That's after you multiply it by 5 plus 1. And then you're going to find your new UFL, which is 28.1%. Just for the sake for the rest, so this is like at 50. So here's UFL 50. Actually, this will be confusing because here, if this the subscript that you add here, sometimes it means UFL temperature or UFL P. Okay, so that is a bit confusing here. So I will write here, this is at 5 atmospheric pressure. I will write that in red. Okay, so this is like at 5 atmospheric pressure. Now, if just for the sake of comparison, I will take the one at 20 atmospheric pressure. And for 20 atmospheric pressure, we are going to find that my UFL P is equal to, you just put your equations, which is 30.6 into 20.6 into log. And of course here you're going to include your 20 atmospheric pressure multiplied to do the conversion. So it will be 2.027 plus 1 is equal to 40.5%. So what do we have here? What do we have? So we can see that it was 13.6. So I have, it's like it was 13.6 here. And let me do it here. Okay. So that was 13.6. That was my upper flammability limit. What happened now? Because you increase the pressure, you raised the bar, and the flammability region became even bigger. Okay, because why? Because my lower flammability limit, okay, did not change. And now what do I have? I have a bigger flammability limit. Okay, and it even can go even bigger. Okay, it can also be bigger. Why? Because the the pressure is even higher. So here's like 28.1% and 40.5%. Okay, just let me write that clearly, 40.5%. And you can see that you just have the flammability region is just increasing more and more. So that is the idea, and this is where if you have increase in pressure, you're going to have a bigger region for flammability. Beautiful. That was a good problem that we had here. Okay, great. And let's see now the next problem that we can solve here. So we have problems 6.5 is done. So now we are going to solve 6.6. Again, we have many components here that we need to solve for. Estimate the LFL and the UFL using the stoichiometric concentrations for methane, propylene, ethylene ether, and acetone. Compare these estimates to the actual values. So let's solve only for methane. So that is 6.6. So I have here problem 6.6, and for methane we want to solve using the stoichiometric concentrations. So what is the stoichiometric concentrations? So we have the LFL equation. If you go back again, just to tell you which equations, you have equations 610 and 611. Okay, two equations, one for LFL and then the other one is for the UFL. So LFL is equal to 55 divided by 4.76 m plus 1.19 x minus 2.38 y plus 1. Okay, so that is the equation, and the UFL is equal to 350 divided by the same story here, which is 4.76 m plus 1.19 x minus 2.38 y plus 1. Okay, great. So this is what we have here. So what we need these values. We need m, x, and y, so that we can calculate what? We can calculate our LFL and UFL. So what do we have here? We have methane, and we need to do the stoichiometry of methane, where CH4 plus O2 gives us CO2 plus H2O. I took the simplest one, you do the rest. Okay, so what do I have here? To balance this equation, the last thing you want to balance is the oxygen, right? So carbon, and first go to the hydrogen one. So you have 4 hydrogens, so you put a 2 here. Now go to the carbon, 1 carbon, 1 carbon. Things are good. How many oxygens now I have? I have 2 and I have 4, so I have 2 plus 2, 4, so I need to add a 2 here. So this is what I have here, and based on what we have done here, if you go to equation 6.9, right, you will know how to do to find the x and y and all those bits and pieces there, and you're going to find out that from equation 6.9, what are the values, please? M is equal to 1. I'll write that again. So M is equal to 1, and I have X is equal to 4, and Y, which is the oxygen, is equal to 0. So simply what I'm going to do now, I'm going to substitute those values here. Okay, so these values are going to come here, substitute them here, substitute them here, and substitute them there. Okay, so after you do your substitutions, and doing your substitutions, you'll get the answer directly. Your LFL is equal to 5.2%, and my UFL is equal to 33.3%. Okay, great. Now to do the comparison here, so to do the comparison, I need to compare it to the experimental value. So what were my experimental values? So these are like my calculated values. Okay, what are my experimental values? My experimental values tells me that my LFL was 5%. Beautiful, that looks really good. My UFL was equal to 15%. So what I can see here, this is a very good approximation. It was predicted well, I would say. However, the second one was not predicted well. So this one, that was a problem in predicting it. So I would say here, my conclusion, this was predicted well, and that one is not well predicted. And this is why I said that we do our calculations, but it doesn't mean that our calculated values are always the best, okay? Experimental values are the ones that we can depend on here. These are not fundamental. They are not fundamental variables. It's not like the density or viscosity. So it depends on many factors that which was difficult for us to find some kind of an equation for that. So we have made some kind of fit using some experimental values. So it's always that we want to generalize things. So we use only one equation for all. So you will always have a percentage of error. Great. So I will keep the rest for you. But the same conclusion that you're going to find even for the rest, that the LFL is going to be accurate, and then the UFL, the upper flammability limit, you're going to have some kind of differences and not accurate value. Okay. So what do we have here? We want to train now ourselves with something different. Estimate the LOC of propane, hydrogen, and methane using the equation 615 and 616. Of course, the book is very kind to you, telling you which equations to use. Of course, when we give you some assignments or in the exam, I will not mention the equations. I mean, you need to do your homework, study, and know which equations to use. In real life, no one is going to tell you which equations to use, right? This is part of the training to teach you and for you to learn. So estimate the limiting oxygen concentration, okay? And this is very important to get the upper and lower limits for pure oxygen, for the flammability limits. So estimate the LOC of propane, hydrogen, and methane using equation 615 and 616. Compare the values in table 6.3. Okay, so we are going to compare the values and say that they are accurate or not. So beautiful. So what do I have here? I have problem 6.7. So this is problem 6.7, and it wants us to find what? To find LOC. What is LOC? LOC is equal to LFL, and then I need to consider what is the mole percentage of O2 over the mole percentage of the fuel. So that is the equation that I can calculate from. And actually we also can do it from another equation, because mole percentage of O2 over mole percentage of fuel, we can get that from the stoichiometry as well. We can get that from the stoichiometry. And if we can get them from the stoichiometry, this became really even simpler and easy. So thinking of it from stoichiometry point of view now, we can see that from equation 6.9, what do we have? We have this equation here, which is CnHXOZ, okay, plus, that is my value here, N plus X over 4 minus Y over 2 gives me NCO2 plus X over 2 H2O. Okay, so this is what we have. This is what we have here as for balancing the equation. So if I would go for my first case where I have propane, right? I have propane. What are the values for propane? My propane is C3H8. So it's like, let me put it here in red. C3H8. So I now can see what is the value of N. I can see what is the value of X. Okay, and of course I don't have Z, so Z is equal to 0 in this case, right? So I have the values of N, X, and Z, and of course I can identify how much O2. Did I miss something here? Yes, I missed something here. I missed my O2. Where is my O2? Okay, so this is O2 here. Okay, great. So I can calculate now the rest of the coefficients here. So the main part that I want to know how much I have for O2. Okay, how much? Mole percentage of O2 over mole percentage of fuel. So now I'm considering mole percentages of O2. So this is N plus X4, X over 4 minus Y over 2, over divided by 1, which is here. So for propane, I already have the values now. The values were N is equal to 3, X is equal to 8, and Y is equal to 0. And by that I can calculate my value of N plus X over 4 minus Y over 2. That is 3 plus 8 over 4 minus 0. The answer will be 5. So I have it 5. So my LFL, my LOC, which was the LFL into the percentage of mole percentage of fuel over mole percentage of fuel over mole percentage mole percentage of oxygen over mole percentage of fuel, which is 5. In this case, this is this 5 here. This will be equal to 2.1% into 5. It is 10.5%. Okay, 10.5%. Okay, so that is how we have calculated LOC. Can we compare it to table 6.3? Yes, please. So at table 6.3, you're going to find that this value, the LOC for propane, is 11.5%. So that is close. That is close. So we are just saying that it is a close value to what was experimentally predicted. And doing calculations, they are good. They are giving us some good indication of what's going on. Okay, so let's do another example just to get the training of this. So part B, what do I have? I have hydrogen. And why I'm taking part B here? Because hydrogen is a little different because it has no C. It has no C term. And this is why it may confuse some people here. So what is the lower flammability limit? It is 4% for hydrogen. Of course, I'm getting this from Appendix B. Okay, so what do I have the values here? If you go to H2 plus O2, giving you H2O, of course, I have no CO2 here, right? And the thing that I have here is H2 plus half O2 is giving you H2O. And in this case, I already have H2, so I can I have the idea that also that N is equal to 0, the C part, the H part, X is equal to 2, the O part, Y is equal to 0. Again, I'm concentrating on H2, right? There's no C, there's no oxygen. And then we go to our beautiful equation, which is N plus X over 4 minus Y over 2, which is equal to 0 plus 2 over 4 minus 0, which is 0.5. And actually, I already know that it is 0.5, right? You see here, I know I already did my balance equation. But this is, if you don't want to do the headache of the balance, you just use this equation here, okay? But if you don't want to use that equation, do the balance, okay? So you do the balance. In this case, I do the balance 0.5, or I can find the value here as 0.5. Either one, all of them will take you to the right direction. And then we are going to calculate the LOC. We already have now the LFL, which was 4%, multiplied by the mole of fuel, or mole of oxygen over mole of fuel, which I found here from the balance equation is 0.5. Okay, 0.5. So simply we are taking, we are trying to find the limiting oxygen here, and we found that it is going to be 2%. If you compare this now, if you compare this to the table 6.3, you're going to find that it is 5%, and now that is somehow they are different. Okay, they are different. So it's not always that things are accurate. For hydrocarbons, many of them they are giving us good accuracy. For hydrogen, we can see that there was a little difference there. Okay, great. So that is what we have here. That is what we have here for 6, 7. And now let's go and see what else we can solve as well. Well, here it says determine the LOC of a mixture of 2% hexane, 3% propane, and 2% methane by volume. And now here we have it by volume. And as you can recall, if you want to calculate LOC, of course I need to get the LFL. And getting the LFL, we need the mole percentage of each one. And so we divide this on the combustible gases. So 2 plus 3 plus 2, which is 5, 7. And then you're going to say 2 divided by 7, that is the mole percentage, 3 divided by 7, and 2 divided by 7. And then you're going to find LFL. And then you want to calculate LOC. Now, for LOC, it's going to be challenging. Why? Because LOC needs the limiting oxygen, right? What is the balance for oxygen? However, I have hexane and propane and methane. I have like 3 different things. Okay? And because I have like 3 different things, it just makes it difficult for me to identify how to find the LOC for that mixture. So we are going to show you how it is done. So 6, 8. So that is 6, 8. And we have a mixture of hexane, and I'll say that this mixture I have is methane, propane, and hexane. And the mixture was the volume percentage here was 2% and 3% and another 2%. If I recall this correctly, it was 2, 3, 2, right? Or I started with methane, 2, 3, 2. Okay, that's great. So based on combustible gases, like this is like 7 total combustibles. I will write here total combustibles. That was about 7% here, and going on. If I want to now find the volume percentage based on the total combustible gases, this will be 2 divided by 7. 2 divided by 7 is, let me write this in a different color. So this is like 28.6%, and now this will be 42.8%, and this will be 28.6%. Great. And just to continue our problem here, do we have our LFL? Yes, we have our LFL for each one of them. Here, the LFL from Appendix B, this was 5%, and this is 2.1%, and so that is like that. So this is in percentage: 5, 2.1, and 1.2. So we have everything here actually, and to calculate the LFL, we already know from the equation that LFL is equal to the LFL equation divided by the LFLI, over YI, and that is the summation that we have. And of course, I don't know why I kept it on the left here, because I was thinking to add them already. So this is equal to 100 over 28.6 divided by 5 plus 42.8 divided by 2.1 plus 28.6 divided by 1.2. So what is the percentage? I already multiplied by 100 here. So this is equal to 2. So this is equal to 2. So I have now my LFL is about 2%. 2%. Beautiful. So what is LOC? I know that LOC is going to be that thing here, which is mole percentage, mole oxygen, right, over mole fuel. The percentage, of course, the mole percentage. And now how to get this value, that is the challenging part. Why? Because we used to get it from balancing the equations. However, how can we do this? Especially that I don't have one equation. I have like 3 species rather than one species, because I have CH4, which is plus 2 here, plus 2 O2, giving us CO2 plus 2H2O. So I have the 2 term here, right? And for propane, it's different. It's C5H12 plus 8O2. Okay, plus 8O2. So now that is also different. And if I go also to hexane, I'm going to find that it is also different. So I hope you already got the idea, right? So it's like not only one oxygen term for balancing the equation, and this is why it became like a different problem here. CO2 plus 7H2O. Okay. So what you need to do here, you do something called normalization, okay? You need to do something called normalization. And normalization, what does it simply mean? It simply means that we are going to consider using what? Using the specific compositions that I already have, okay? The specific compositions that I already have are these ones here. These ones here, okay? So these are the percentages that I have, which are already normalized if you sum all of them to 1. So I'm going to use those conditions there. And using those conditions, what does that mean? It means that now my equation here, instead of CH4 plus 2O2, it will be written as 0.286, that is 28.6%, CH4 plus 0.572 O2. Okay, so like multiplying by 0.286 for the whole equation. And of course, you're going to continue the problem. This gives me products, whatever it will be. I don't need now to see those numbers here. Okay, so and then we go to the second one. I have 0.428 percentage, okay, of C5H12. And if you multiply 0.428 the whole equation, this will be 3.424 O2, giving me some products, whatever they are. And if you go to the third one, I have 28.6 of hexane, C6H14, and if you multiply by 0.286, again this will give me, now it's multiplied by 19 over 2. So 0.286 multiplied by 19 over 2, it will be 2.71702, giving me products. So what do we have here? If you can consider that this as fuel, this is fuel, right? So the sum of all these fuels is 1. Okay, so that's the idea of normalization. The sum of all those fuels here, if you sum them, that will be 1. And then you're going to sum these O2 to get an idea about how much O2 do I have. Okay, I hope you got that, right? So it will be like one fuel plus 6.713 O2, giving me products. So what I have 6.713 O2. And now my problem became straightforward, where I can say that my LOC is equal to the LFL of the mixture. Okay, the LFL of the mixture, if we just go back, my LFL of the mixture was what? Was 2%, okay? So we go down here and we say that is equal to 2%, multiplied by the number I got for oxygen, which was 6.713, and that will be 13.4. And that is my answer, okay? That is my beautiful answer here after we have done our calculation. Great. Well, there is another approach, by the way. I mean, instead of going through all of this, because there's like an advice given by the book saying that Well, just take the other approach is just to take the LOC of the pure species with the lowest value. Okay, so what it is saying is that just take LOC of the pure species of the lowest value. And if you go and look what is the lowest value of all, you're going to find that the propane, it had the lowest value. And just taking the LOC of the lowest value, if you go to table 6.3, you're going to find that LOC for propane is equal to 11.5%, which is less than the others, which was 12%. Of course, this is not an exact number when we have 13.4%, but I'm just telling you that this is like another approach just for an approximation, very quick approximation of how to do it. Great. So that was 6.8. That was 6.8. Okay. So what we have now, we have some other problems to solve, which is 6.9 and 6.10. But I think so what we have done is now is about an hour. So it's good enough for what we have gone through. I thank you very much, and I hope that you have gained from what the problems that we have solved. We are not going to solve all problems, but this is like the training part. So this is why we had put an effort to solve these problems. So till then, thank you very much. Have a nice time and good luck. Good luck. Oh my nose is not that good. Now it's better. So thank you very much. Okay, good luck. Ma salama.